Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about PCB motors. So let's dive deep into it. Now, what exactly is the problem? Well, problem is that we have been using motors for a very long time. As in, the oldest variants are put in museum, and I mean we have been using this puppy for 1 century. So it's not a new technology. Technically, it's classified as ancient technology. So we use motors, and we use a lot of them. How lot of them? Well, around billion plus motor, and there is a very good saying that generally those many motors are active at any point in time. And it's not only including like big daddy motors, they are also tiny baby motors. So we have lot of motors, like a lot. So what does that create? Like what's the issue with that? Issue is that because these puppies are hungry, they consume a lot of resources while we are making them, and they also consume a lot of energy while they are running them. So it's not like, okay, once you build it, it's gonna last a long time. Yeah, it do last, but problem is like its running cost is very high. It's like an air conditioner. Even if you can buy an air conditioner that runs for a very long time, the energy bill is not kind. So it's the same thing with motors. So that creates a scenario where we are using so much motor that and making so many of them that if we can have even few percent improvement, let that sink in. I'm not talking big daddy improvements, I'm talking tiny improvements, as in like, oh, this motor is like 0.5% better. That sort of improvement translates to a huge gain. And for some many industries, corporates, those are like, shut up and take my money. And even from a nation's point of view, if whole nations upgrades their let's say sloppy induction motor that is used in ceiling fan to something better, let's say BLDC motor, even though it will cost more, the energy demand will go down. So it's a very significant thing because of the use and ubiquitousness of motors, that any small benefit that we can gain, it's worthwhile pursuing. So what's the logic behind it? Logic is that iron bad. So why do we use iron if iron equals bad? Well, iron allows us to have coils of wire in like it also allows us to have a physical shape, and in using that physical shape and the fact that iron is conductive, more conductive than air for magnetic flux, it concentrates those puppy. So that's awesome. It allows us to concentrate magnetic flux, improves yield, awesome, torque, awesome, but does come with a side effect known as this puppy, that is induction, basically eddy currents, induced eddy currents. And to make sure that these eddy currents do not become a hassle for us, we have to use plates. Now, using plates increases cost. That's why we use laminates. These are not forged part. They are like basically stamped sheet. You stamp a lot of them, you stack them, and then voila, you have that puppy. But it does cause losses. While you reduce basically eddy current from a huge eddy current to little eddy currents, you still have eddy currents. This puppy will heat up if you run them for long. Like for example, cement plants or many of the manufacturing plants, motors could be running for days. In those sort of time, those stators, yeah, they start to heat up. So that's a serious issue. Then we come to another naughty part of iron, is that wherever you have iron teeth, so to say, or slot, whatever you want to call them, they act as a naughty points. So when you have stuff moving, basically rotor moving, so your rotor could be like acting like an electromagnet, it could be electromagnet, it could be a permanent magnet, whatever have you, but it has something that is moving while having a magnetic field. So that's awesome. When you are going from coils to coil, that's awesome. But here's the, you move through it, right? You have coil, and then you have basically slots, then you have coil. That's why you see lines there. Problem is, the moment you go through that, it jerks. Now, if you amplify that effect, we call it stepper motor. And if you know for a fact that stepper motors are not very smooth, that's the reason behind it. Stepper motor just amplifies the cogging effect. Now, how the heck we do not know about this cogging effect? Well, you know about it, especially if your motors are running very slow in low voltage or something, like you feel like it's not smooth. So the only way engineers can bypass this is basically make it heavy. So not even heavy, it's like it's a inherent fact of once the rotor starts spinning, once it has inertia, it just bypasses it. But there is always a frequency attached to it, meaning there is a vibration induced into your rotor because of this cogging effect. Of course, it's very little, but it does hurt your bearings. Not on day one, but day 300, it's like your bearing is like, bro, come on, it's annoying, man, I cannot take this. So it's one of those things. It's not a long term, basically it's not a short term, your motor goes boom. It's long term, your motor life shortens. Like your motor cannot inherently last beyond a certain point simply because bearing would be compromised because of the cogging effect. And of course, it won't be the only thing, there would be other things also. But these are little things that pile up to a huge hassle. Then it is vibrations. Again, vibrations are not just only bad for your bearing. Vibration inherently mean you are losing energy, so loss in the system. And why the heck these puppy die? Like, what is the 100% common thing? Like, if you take hundreds and thousands of motor, what would be the one common thing that would have been broken all of them? And you go like, is there only one thing that breaks? Yes. Where it breaks, that's a different thing. But there will only be one thing that breaks. Unless you have like physical damage, like something physically destroyed it. Electrically, I'm talking, you will always have insulation failure. Where the heck that happens, that's up to you. That's on the motor design and all that jazz. But you will always have one thing, insulation failure. So whenever these puppies go poof, they generally lose their insulation. Now, why the heck insulation is such a problematic thing? Well, we have raw copper conductor. Awesome. We don't want this to short it out. So we dip it into a basically a liquid, so to say, that coats it. Now, coating is inherently not a very stable process. It's not like I say it's this micron thick, that means it's micron thick. Nah. It's like you hope for it. You try to. You get your tolerance right. But it's not like what you call absolute science. It's like we guess within tolerance, good. So we do that. Then we poke this puppy with having insulation paper. Then we have poke this puppy. You poke this puppy. Now you put so close to each other that creates a hotspot. Now, problem with hotspot is that hotspot itself is not an issue. Meaning, if this part gets 70 degrees Celsius, that's not an issue. Issue in this puppy, basically the part where they turn. First, not only they are basically unconstrained. So you have a constrained part that's not gonna move, and then you have vibrations. So it's like very locked. It's like I got this. Then the top part, this part, that starts to vibrate little bit. It's not really like bam bam. It's like little vibration. So that creates an issue. Then you have the fact that these are exposed compared to this that are compacted. So they change in temperature. Consequence, not now you have something that amplifies this erosion. Now you have something that is vibrating versus attached to something that is not vibrating. Basically, it's like this. This is vibrating, this is not vibrating. This is hot, this is cooler. So that stress point, generally, that's why things, insulation generally go poof in this area. It's not necessary it has to go there. It can be deep in the slot also. But that's the primary failure point. Meaning, if we could ever create a technology that allows us to turbocharge our insulation, we're going to have a stator that's going to last. And I mean last for centuries. It's actually doable. If we can have a scenario where stators are like damn awesome. So some engineer was like, hey, didn't we build PCB for that? Voila. So we take that, squish this puppy into PCB. Now, PCB also has another advantage because you are layering them layer by layer, and each insulation is far more stronger compared to that enamel coating. You can increase the voltage or amps also, depending on your design. You can have much thicker traces, up to you, completely your design. And compactness, basically how much copper you have per square inch area or per square millimeter area. This puppy can exceed this, meaning this, let's say, has X, this could literally be X plus 20%, or X could 2X. So fundamentally, this has much higher density of current when you're running this puppy, meaning this and this has same power rating. Yeah, that's the difference. Having the ability to A, insulate copper better, B, having so much of copper so close to each other. Even though this has more copper, this has higher copper density, inherently meaning you're gonna achieve basically more with less copper. That's also better. So current density is ludicrously better. Does not have the caulking, does not have the eddy current losses. So it has some true advantages. And let's not even talk about sizes. So what were the design? Well, right now, every company that I have looked into, they are generally building a BLDC that is axial flux. That's all they are building. It's like axial flux design. Can you build a radial with this? Maybe, but it's not well suited for that. So you have to go to axial geometry. Now, because of the fact that these puppy have very high density, it can even turbocharge the density of axial flux motor. Axial flux motors are already high density compared to radial. So radial is here, axial is here, and this puppy is like, that's how tight this puppy can be. So what about the PCB material? So PCB is made out of FR4. Now this is an umbrella term that simply signifies flame resistant mix of fiberglass and basically epoxy. Exactly like how you build concrete roof, you have like cement and you have basically rebars. So rebar job is done by fiberglass cloth, and basically that's providing the main bulk of material, and then you have epoxy resin that's providing the strength of the material. Like, not strength would be correct, but stiffness, basically like the stiffness is coming from that. Fiberglass is like, I got the strength, I can withstand the pulling. Exactly like how we have rebar and concrete. So this is a composite PCB. Be mindful, this is a common thing. This is exactly how your high quality motherboards are built. This may change, by the way. FR4 may change to something else, but that's the inherent idea. You have fiberglass cloth and epoxy resin. Quality of that epoxy resin defines how resistant this puppy are. These puppy can easily work at 100 degrees Celsius plus continuously, meaning if you're running them and they're like, bro, I'm hot to 100 degrees Celsius, they're like, bro, I got this. That's within its working temperature. You do not have to worry about it. Unless it crosses 160 degrees Celsius, this puppy is like, I got this. and they are 2 to 3x smaller. I specified radial, axial, this puppy. Very small. And because again density, it does have high density, so it does not get same mass savings, but it does give minimum 50% savings. And some designs have even more savings. Like bigger you make it, the more savings you get. So if you are talking about like 200 horsepower motor, not that much saving. You are talking 500 horsepower motor, now we are talking a lot of saving. So you get size savings, you get mass saving. And they are using multi-layer PCBs, generally very high count of multi-layer. I mean, like they don't even start at 4, they start at 8 and go to, let's your imagination go. And that's how they achieve ludicrously high copper density, ludicrously high current density, and smooth flow. So no caulking, so bearings last much longer. And because of the design and inherent benefit of axial flux, they do not even have bearing current, so bearings last exponentially longer. Now, what about the winding design? They generally use 2 core winding designs, that is lap and waved windings. You will rarely find this design. These are generally done for amateurs. They generally have waved designs and lap designs for more oomph where they need it. So that's the design aspect of this puppy. Are there any products of this? Well, yes, there are companies that are working on it, and I have looked into those companies. You cannot call them, you cannot email them, ask them for just give me one product, because they are, all of them are working for OEM status, meaning they want to be the one that provides motor to everyone else. They're not looking for like, I build a company that I sell the motors. They're not working for that. And it kind of makes sense, because like as a starter, that's the only way you can have bulk order on day one. So they are doing that. Now, what are these companies offering compared to all other manufacturers? There are hundreds of manufacturers of motors, and many of them are very well established. So what are these puppy offering? They are offering tailor-made, meaning custom built to your exact specification, meaning they're not like, even if you can select a geometry, let's say you selected, hey, I'm gonna use this sort of motor design, let's say BLDC axial flux motor, you selected it for your truck, awesome. But here's the, how many slots? Now you'll be like, I can change it. Yeah, you can change it. Problem is that will take time. Here, you're like, hey, I want this many design, done. Control C, Control V, designs have been printed, PCB would be manufactured. By the time 1 week, you can get that, like physically delivered to your place. And then you're like, you know what? If you are a wise engineer, you will be like, if you have narrowed down your selection, it's like, hey, I think I need 6 pole, I need 8 pole, or whatever have you. You will offer all of them, and then you will get all of that. You keep changing the plate until you find the precise match. It's very precise. It's not like it's close enough. It's not like you have a catalog and you're selecting it. It's like, what exactly do you need? It's a tailor-made solution. That's the company's motto from ECM PCB Stator Technologies and basically Infinitum Electronics PCB Stator Designs. They really have weird names. So they are doing it. Tailor-made, and you can stack them, meaning this design, you can see it has 3 PCB. For example, if one PCB can, let's say, handle a few 100 kilowatts, and you're like, no, we need even more, like let's say aircraft, you need a bit more than that, you can put 2 PCBs. And you're like, we need even more, put 3 PCBs. So that's how you can stack them. And because you can stack all of them in one chassis, because again, physically they are much smaller than axial motors stator, so it can be put into a much smaller area, much higher power density, and you can get much more oomph out of it. Now, at that point in time, you reach into another limitation. While PCBs are there, while PCBs are thin, meaning it can dissipate heat into radiant environment very well, still limited. It's you can because again, the PCB that is surrounded by other coppers, basically like PCB layers. So what about the layer that is sandwiched in right middle? It will take time, and while copper is there conducting heat away, it's not going to be very efficient. So they have oil cooling option, meaning if you need megawatt class power rating, that point you have to go to oil cooling. And because again, PCB does have very thin layers, you can just wick all the heat away very effectively. And that's why you will always see such a giant copper traces around them. Those are sort of heat weak areas. Even for air they will work, for oil also they will work. That will allow you to have ludicrous power density. Now, does that matter? Yes, many of these companies are building motors for elevators. Now, why does that matter? Well, here's the deal. If you are talking about an elevator shaft, you have a motor that is, let's say, 2 tons. That means you need substantial structure, steel structure that can handle that puppy. Imagine somebody came to you and it's like, bro, instead of 2 ton, I'm gonna give you a motor that is, let's say, 300 kilograms. What's the difference? First, it's super easy to transport to a tall building. Second, the substructure that you have to build would be much more relaxed, much more relaxed. It will only be for the box, the cables, the gear, safety margin, and the motor would be like, brah, minor. So That's why there is a significant advantage if you can have very high density in very small sizes. And if you're talking about EV trucks, where you need some GG amount of power, this is the easiest way to achieve it in small size. And for EV aircraft, it's a really useful thing. So there are companies that are producing, and this guy even has Indian CEO, which is becoming a common trend now. So it's one of those things. So what we can expect in the future? Well, here's the deal. Whenever I'm talking about motors nowadays, you have to understand this. We reached a maturity point. At this point, anybody comes to you, is like, we're gonna make twice as better motor. It's like, no, bro, no, just no. That's not happening unless you break the laws of physics. So what we can achieve is only better tools, meaning fine-tuned tools. Like, which is the best motor topology that I have seen so far? I've seen so many motor topology. Which is the best motor topology? The cheapest, the most robust, I don't care about the motor. That's induction motor. That's like solid, robust. I don't give a damn, especially if you're running it on 3-phase. It's like, bro, I got this. Then what about the motor that my personally favorite? That is brushless synchronous motor, AC motors. Why? It has the basically rotating part has an electromagnet into that, meaning you can control the EMF of the system, and it allows super high efficiency. And here's the deal: it can bitch slap BLDC in low RPM torque, and it can bitch slap basically synchronize asynchronous motors, not synchronous, reluctance motors with permanent magnet assistance. It can bitch slap that at high RPM, meaning this motor has the widest category. Meaning if you can afford this, put it in your car is like, bro, I got this. You do not discuss. It's like, bro, I got this. So even that topology can be put into this also. It's not impossible. There's nothing in physics that's saying you can't do this. So it's just a topology change. Like same way we change from radial to this, we can go from this to other configurations. Like right now, most are building BLDC. You can build other designs also. Although it does not make sense to make a reluctance motor because they are inherently vibrationally, they vibrate a lot. So you do not want that. So it's just a wise technology swap. Like somebody looked at it, it's like, hey, we have so many things already figured out. We have motor drivers sorted. We have PCB manufacturing 60 years sorted. We have casings, we have axial flux design sorted. We have demand in the market sorted. Everything is sorted. Somebody is just like, hey, take the coppers, squish it into PCB. So it's a wise use of technologies that we already have. It's not a new creation. And they are showing this demo where this big puppy was built for some big motor, and they're like, what about the central PCB? You have to throw that away. They're like, no. They designed a motor that is around 1 horsepower that is made out of cut out of the center area. Wise. So do be mindful when you are looking into this sort of ecosystem. And like, again, imagine having this sort of tiny motors when you're talking about robotic arms. Your robotics arm will become exponentially lighter. Like, why? Robotics arms are designed for the last actuator, meaning things that are touching other things, that's the main puppy. You design everything around it to make sure that puppy works. If that puppy is lighter, the motor that is in this second joint also becomes lighter. Now this joint also becomes lighter. Everything becomes light. So that's why a robotic industry loves if you can give them high power density, reliability, robustness at low cost. And given the fact that this thing is inherently light, as in like inherently has less mass, it's like, shut up and take my money. And this can be swapped also, because let's say mechanical parts, they last. This puppy, let's say you fry some electricity with surge current. Surge current can go to like 10 kV, 50 kV. You fried this puppy. Again, this thing is robust and not indestructible. So let's say you fried it, it's like swapping, just a very swapping thing. So from robotic arm manufacturers, they are heavy breathing right now. It's awesome, but do not expect energy running cost will not change that much. So because be mindful, we are already at a point 90% is given. It's like plus 90 we have a discussion, but that's not going to make a big change on your pocket change. However, the USP of compactness, lightweightness, and the fact that it consumes less copper, uses less iron, equals profit. That's a big thing. The fact that only this much copper is needed for making very high energy density motor, that's a big deal. Copper is not cheap. That is not cheap, flat out not cheap. So whenever you are looking from an EV point of view and you are talking about like, I'm going to make 10,000 of that amount of power saving directly translates to some big money. Having a lighter motors in your EV directly translates to better range. So having less iron, again, fundamentally reduces your cost. Having less mass and volume means how the heck we ship everything around the world? We use shipping containers. Now imagine it this way. You have a shipping container shipping from ABB to, let's say, a place in India. That's going to take a while. Now that box is limited. That box is standardized. Shipping container is standard. But imagine it this way. They can give you this motor and put twice as much. That's awesome. That reduces your cost. Imagine the copper cost goes up, but this does not go up that much simply because it's using less of it. And let's say the motors, if companies want to, they can design in such a way that stator replacement would be very easy. Like it can be designed in such a way that stator, this cassette coat can put, it can be replaced quite easily. So even if you have a downtime, you just yeet this puppy out, put a new puppy in, you're back in game. And be mindful, this does not have bearing currents, does not have torquing, basically jerkiness, so bearing should last exponentially longer. So it's a really wise tool of technologies that we already have, making sure these puppy make love to each other, basically stator making love to PCB, and then voila, we have a tiny baby that can provide a lot of power in very small space. And while reducing our CO2 emissions simply because it's consuming less energy to make them. So this was my presentation on PCB motors. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.